morning's speaker is Dr. Sphiwe Skhosana. He got his PhD, he completed his PhD last year at the University of Pretoria, where he did his undergraduate and his postgrad studies. He is currently an NGAP appointment at the University of Pretoria. Come, would you like to present?
Thank you, Bruce, and thank you, Diane, and the CoE-MaSS team for the invitation to give the seminar. So just to check. So my presentation today will be about work that I did for my PhD project under the supervision of Professor Millard and Professor Kanfa from the University of Pretoria. So we were concerned with addressing a problem that occurs when you estimate a mixture, a non-parametric mixture of regression models, and that problem is called the label switching problem. And we proposed two approaches to addressing this problem. And today I'm going to talk to you about one of those approaches. And this is actually one of the approach that I prefer the most. The first one is good, but this one that I'm going to tell you about is actually greater than the first one. The first one works, but this one is great. And the reason for that is because it actually integrates well with the idea behind mixture modeling, because it looks at the unobserved, the missing information that is involved. And I will just before give a background of what is a mixture model. So I will just now talk to you about the outline, or give you the outline of the presentation. So we'll look at the background, and then afterwards we will discuss the model that we are trying to estimate in this presentation. And next we will look at an estimation procedure. And this estimation procedure is the one that leads to this label switching problem that we're trying to address, just to demonstrate where is the problem coming from. So once we have shown where the problem is coming from, we will be able to discuss the method that we proposed to address this problem. Thereafter, I will show you a couple of numerical examples, simulations, as well as an application in environmental economics. Then I will close the presentation with a few words on how whatever I'm presenting now, how can it be extended, and what are we looking at currently with the team. So I will first give the background of mixture modeling, or mixtures of regressions, which is just a special case of mixture modeling. So what are mixtures of regressions? Mixtures of regressions are simply regression models for data that comes from subpopulations, that are unobserved. So you have a population, and this population has various subpopulations. Unfortunately, you don't observe these subpopulations, and mixture models are useful in that scenario. So I'll give an example, and the example is, suppose we are trying to explain or understand the dependence of wages, salary, on years of experience, right? And we know that based on your education level, the wages and years of experience relationship will differ. For a person who has, for instance, a bachelor's and one who has a PhD, for instance, they will earn different salaries, even if the person with a bachelor's has more experience than the one with the PhD. So if let's suppose that you do not observe this information, you don't know whether the person has what level of education the individual has. So what happens usually is one would just estimate a single regression model to explain the relationship between wages and years of experience, right? And in my opinion, that will be misrepresenting the data because there are these different groups that exist within the population. So if you don't actually model the groups separately, you are actually misrepresenting the data. Another example that I'll give, I usually give this example, and it's on, let's suppose we are trying to explain the relationship between blood pressure and BMI. So, and we know that there is a specific gene, a genetic factor, such that if an individual has it, then as their BMI increases, their blood pressure accelerates. Whereas if they don't have it, there's the opposite, or the increase in the blood pressure is lower. So there are two different relationships in that scenario. But let's suppose you don't observe the genetic factor. And if you don't observe the genetic factor, what usually happens is the health sciences will call a statistician, and the statistician will fit a regression model, just a single regression model, ignoring this unobserved information, which again, in my opinion, it's misrepresenting the data. So these are some of the examples in which mixtures of regressions can be useful. When you have these latent groups, or these latent, or the latent variable. So how do they operate? So mixtures of regressions, they assume that there are a finite number of latent groups, unobserved groups, and for each and every one of these groups, they fit a regression model, right? And each and every individual, or each and every observation that we get from the sample, we collect the sample, each and every observation has a specific probability of having been generated by a given regression model. So in this schematic here, or in this function, we have k component regression functions, right? So all of them are fitted for the different latent groups, right? And as you can see there, a given observation, so a given observation has a probability represented by pi of having been generated by a given model. So this is a probabilistic structure that is applied by mixtures of regression. Usually what happens is in regression, we have to talk about what the error distribution, what is the error distribution? The error distribution, if you have a continuous response variable, the error distribution is normal. So that's, if we assume that, then we have what is called a Gaussian mixture of regression. So Gaussian is normal. So that's where the Gaussian comes. And another way to represent the Gaussian mixtures of regression model is given there in equation 1. Right? And the Z there gives you all of the possible covariates, all the possible factors that can explain Y. And that linear combination there gives you a compact form of the mixture of Gaussian mixture of regression. And the pi there, which is our probability that an individual was generated or belongs to a specific latent group, is also referred to as a mixing proportion. It's the relative size of that group. It represents the relative size of that specific group, whichever that group is. Right? And there we have also the regression function. The regression function is the one that's given by that function M. And typically the regression function, one would say there is a linear relationship. So within each and every one of the latent groups, we can assume, or typically what's done is we assume a linear relationship, and that's what we have there. And so this model, the form of the model that we have on the slide, was actually proposed or introduced by an economist, and exactly as it is. And if you want to know more about it, there is a booklet that actually speaks about mixtures of regression. So next, I want to talk briefly about the contributions that we made to mixtures of regressions, and those actually concern the lack of flexibility in the mixtures of regression. So as you can see, the mixtures of regression, it has certain assumptions in terms of the functional form of the different parameters. For instance, linearity in the covariates. So the linear relationship is sort of like it's a limiting factor. So what we can do is we can add a bit of flexibility to the model, and that's what we have proposed to do. And what we did is we instead said that the parameters of the model are non-parametric functions of a given covariate. So non-parametric smooth functions. So we don't actually specify any functional form for these parameters. We just say they're just smooth functions. And smooth will be something that I will clarify in a few slides. And what we have is that model number 2. And I just want to say that it's not, the model was not actually proposed just for theoretical purposes. It's actually very, very much applicable. So, and I will try to go through each and every component there. If we look at the pi, so the pi is a function of S. So the pi is a function of S. One can actually think of this as in our wages and years of experience example. Of course, we know that an individual having a degree depends on one's family income, right? Where do you stand in terms of your standard of living? So for high income families, you are more likely to have someone who is more likely to have a higher degree, let's say a master's or a PhD. But for people who are from less well-off families, they are less likely. So you can say that the probability of belonging to a specific group is actually a function of the family income, right? And so that's how that actually factors in. Another thing is in statistics or in regression, mostly what we have is we have a phenomena called heteroscedasticity, which is simply saying that the variance is a function of a covariate, right? The variance changes as the covariate changes. So usually the assumption is that the classical regression assumption is that the covariate is always constant, or the variance is always constant. But you can actually have cases where the variance is a function of another covariate. And that's what that variance, this part here, that's what it covers. It covers that situation. And we can also have the regression function being a non-parametric function as well. So we have the parameters, the regression parameters, the features as functions of some other covariate. It could be, for instance, time, right? So as time goes, at different time points, the slope or let's say the intercept changes, right? So that could be something that is useful in that situation. Of course, in reality, there's no such thing as linearity. So that's what that part there. These are additive functions, the G's. So they're univariate additive functions and they're non-parametric. And so those functions can actually take any form. And non-parametric just means it's a smooth function, but we actually have no idea how it looks like. But we make some simplifying assumptions so that we are able to get an estimate of it. And this is actually where this is how this model is useful, right? It looks like it is a general model, but it's not really, it wasn't actually proposed just for theoretical purposes. It's actually very much applicable. And it's made up of many special cases, and some of those special cases have already been proposed and they have already been applied in the literature already. So next, what we will do is we will just zone in and just look at a special case of that general model. This is just to illustrate the idea that we have for addressing label switching, right? And so what we do is here we just consider the case where the mixing proportion, that is the mixing proportion, the probability of belonging to a given component is a function of some covariate S, right? And that's the only change that we make from the Gaussian mixture of linear regressions, just to simply illustrate the idea of that we have in terms of addressing the label switching problem. So just to have a single non-parametric function, which we have to estimate, and this will show us what exactly happens if we do not actually take into account the label switching problem. So here, this model is called, it's a Gaussian mixture of regressions, and it has a varying mixing proportion. So varying it implies that it's a covariant varying. So it depends on some other covariant. And this function is non-parametric, and this will be clarified later. And we assume that we know how many latent groups there are. So the K there is known. In our presentation, in my presentation now, this is what I'm assuming. I'm assuming that K is known. Of course, in reality, in practice, it's not known, and one has to estimate. But this is not the what this presentation is about. Okay? We just assume it to be there. But of course, this can actually be found using information criteria, using either the AIC or the PIs, which is something that we will illustrate in terms of our application. So now we have the model, and we go to the population, we collect a sample of size n. And the sample of size n has x, the covariates, s, another covariate, and y, our response. And we have that likelihood function. So that likelihood function on equation 5, it has to be maximized for us to obtain the parameters var theta. So that includes the parameters as well as the non-parametric functions. As we remember, the pi k there is actually a vector of non-parametric functions. And so we have to estimate this var theta. So here we have two components. We have a parametric component and we have a non-parametric component. And we have to estimate them somehow using the data. Of course, we know that for non-parametric, you have to make use of data within a specific neighborhood. So you choose a neighborhood, you estimate within that neighborhood locally. But with parametric, you have to use the whole data set in its entirety. So now we have two conflicting situations. So how do we approach estimation in this particular situation? So in terms of estimation, what we will do is we will instead assume we will have a two-stage approach to estimating both of the parametric as well as the non-parametric. So how does this two-stage approach work? So the two-stage approach says that in the first stage, I'm assuming that all of the parameters of the model are non-parametric functions. And once I've done that, I can only estimate all of them non-parametrically. I don't have to estimate the parametric and the non-parametric separately. I can just do them once. And then once I find the estimates for the non-parametric, I can use them. I can use the estimate for the non-parametric to get the parametric. Right? That's in the second stage. So first stage, I get the parametric, the non-parametric functions, and then afterwards, in the second stage, I maximize a likelihood such that it gives me the parametric estimate. Right. So that's the two-stage approach. And before we go to the two-stage approach, I just want to clarify the non-parametric. The non-parametric, what does it mean? What do we mean by non-parametric? And this whole non-parametric idea comes from Taylor's expansion. So Taylor series expansion, so it says that any smooth function can be locally approximated using a polynomial of some degree, any degree, right? So now we have to assume that is a certain function or a given function that we say that is a non-parametric function. It has a given number or it has a specific continuous derivative. So that's p plus 1 continuous derivative. And this derivative exists at a location, at a local point in the domain of the covariant. So that's the assumption that we have to make. And once we have done that, Taylor's expansion says that we can approximate the function at that local point using that linear function there in equation 6. Right? And this equation 6, I can rewrite it in the form that is given in equation 7. Right? And the form in equation 7 actually shows that this is a linear function that is usual to everyone, or normal to everyone because you have the intercept, you have the slope parameters, and each and every one of those is associated with some form of covariate that is made up of, that is obtained at a specific location. And how do you get the function at the location? So what we do is you have to estimate that linear function in equation 7. So I have to estimate that linear function in equation 7. I get the parameters beta 0, beta 1, and beta p. And once I have those parameters, I can estimate the function at this point here. So this is regardless of what p is. So I have to set p. That's the assumption that I have to make. And that's the assumption about the continuous derivative. Which derivative do you have? Whichever assumption you make about p, this will always be your estimate at the end. And we can actually take a group of local points within the domain of S and do this exercise again for all of those local points. And once we have the estimates at those local points, we can join them together using interpolation to get our final function. And so this is what we mean by non-parametric, and this is the context in which you have to understand these functions here. So this function here, it's exactly what we had in the previous. It's exactly this situation here, f of u. Just that in this case, it's for a specific component or a specific latent group. And we have here a local, this is a local, locally weighted likelihood function. Locally weighted because you are actually doing the estimation at a specific local point within the domain of as the covariate of the function, right? And the weighting function is actually a kernel. It's called a kernel, and you can choose any kernel. You can choose, but usually we find that the Epernechnikov kernel works better than other kernels. But the Gaussian kernel also can be used. But there is actually a theorem in a book by Fan that actually says that the Epernechnikov works better for doing non-parametric regression. So that's what we do. We just maximize. We choose a set of local points within the domain of S, and we maximize that function, that likelihood function, at each and every location. We do it individually, right? And then we get this part here. So these are estimated at each. So this is what we have somewhere. Yeah, this is the one, and we are doing it for each and every local point. And once we find the estimate, we can use interpolation, linear interpolation, Lagrange interpolation to get the functions that we are trying to estimate. Now I have the functions. That's the first stage. The second stage, I have to maximize this. This is a global likelihood function because these parameters, beta and sigma squared, the regression parameter and the variance, they are global parameters. So I have to estimate them using all of the data. So I use this function that I found in the first stage to get the parametric term, to estimate the parametric term. Right. So these two, these are the ones that we have to maximize. And in terms of maximization of those two likelihood functions, unfortunately, we can't actually do that in an analytical. There are no closed form expressions for the likelihood estimates. Even the local likelihood estimates do not have closed form expressions. And why is this? This is because we have that missing information situation. So we don't actually know. We don't have the indicator of where each observation. We collected data from a population, but we actually did not collect. We don't know where in which subpopulation it belongs. Where did we get it? Which subpopulation generated this data point? We just have data from a population. We just cannot actually separate it and say this is from latent group 1, this is from latent group 2, and so on. And so because of that, we cannot actually have the closed form expressions for the MLEs. So what we do is we introduce this information that is unobserved as a latent variable. And we say that we call it Z. So Z is it's a vector. For each observation, we have that Z, and Zik, where I is the observation and K is the latent group or component. If Zik is equal to 1, then the ith observation belongs to the kth group. Otherwise, Zik is equal to 0. So this is a k-dimensional vector that has 1 at one of the elements and 0 elsewhere. And once we have that, we call the data complete data, because now we have everything. We know which component generated which observation. Now we can use that data to construct another likelihood function. So we do it for both the local as well as the global, right? So it's these likelihood functions, but now they actually include that additional information that we introduced as a latent variable. Now we have to maximize these two. They can actually be because you can find closed form expressions, but unfortunately you cannot get them analytically. You cannot maximize it. Why? Because again, you did not actually observe Z, right? So you have to do it numerically. You have to maximize these complete data log likelihoods numerically. And how do we do that? There is a really famous and interesting algorithm called the expectation maximization algorithm. And the expectation maximization algorithm, it proceeds in 2 stages. In the first stage, it calculates the expected value of the complete data likelihood function. So complete data, the likelihood based on this data set. So it gets the expected value of that likelihood function. And in the maximization step, which is the second stage, it maximizes that function that it obtained in the first stage, the expectation stage. And then it iterates until convergence. And that's where we can find our MLEs. We have to do this numerically, and the best way to do it is to make use of the expectation maximization algorithm. So it is way too easier for us to maximize the complete data likelihood for the global function, for the global likelihood function, but if we actually do this for the local likelihood, maximizing each local likelihood function, each complete data local likelihood function, we may experience a situation called label switching. And I will now proceed to illustrate how does this actually come about, the label switching problem. So we have, that's our complete data log likelihood at each and every location within the domain of X. So we have the covariate S, and we go into S and choose certain points within its domain. And using those points, we maximize this function at each and every one of those points. And we just have to note that at this point, we have Z, but we didn't observe Z, right? So how do we actually get Z? Of course, the EM algorithm. So this is how the EM algorithm proceeds. So at the rth iteration of the algorithm, as I've said already, you will calculate the expected value of that complete data log likelihood function, right? And that actually just it reduces to calculating this probability. This is a posterior probability, which is referred to as a responsibility, right? It's the responsibility that the kth component takes for explaining the ith data point. So that's what we call it. We call it the responsibility. And I want you to take note of the fact that this is actually being calculated at a specific location, just that location. It's a specific one location, right? And we have to do it at all of the locations so that we get our function at the end. Now, once we have that posterior probability, which is equation 12 there, we exchange or we substitute that posterior probability for Zik. And once we have that, okay, I moved too fast. All right. All right, all right. Not bad. All right, yes, we're here. We're back. All right, so we have at the maximization step, what we do is we maximize given whatever we've obtained in the E step, the expectation step. And this actually just shows us the estimation at a specific location only for the mixing proportion function. Of course, we have to do it for all the others, beta as well as the variance. But this is just to illustrate how will it work for a specific function and at a specific location. So this is what we have. So this is the E and the M step of maximizing this function here, right? And it happens at different locations. So at different locations, so U here, it's just a set of all of these locations that are within the domain of the covariate. And again, you have to note that this is actually happening at different locations. We are estimating or we are calculating the same thing, but at different locations. And that will actually come as a factor in what I say next. Let's suppose you have two components, two latent groups, right? And this is your mixing proportion function. There's a true function and there's an estimate. This is ideal, right? Let's say you went through the expectation maximization and you got these estimates here, right? This looks good. It actually it got the estimate as the true functions are. So they are close to each other. But that's actually the ideal case. In practice, what you will actually observe is something like this. And this is the label switching problem that happens. And to understand why that is happening, we have to come back here. And that's equation 12 there. So equation 12, if you remember, it actually calculates the responsibility, that is the probability of the ith data point belonging to some other component K, right? Let's suppose at different locations, we have two locations, location 1, that is U1 and U2. Let's suppose that at location number 1, instead, the ith data point has a higher probability of belonging to the first component, whereas at the second location, it has a higher probability of belonging to the first component, right? So you have information about the same thing, but it's different at different locations. And as a result, what happens is if you take this thing here and put it there and estimate this function, what you will have is something like this, right? So this is the label switching problem. It's because at different locations, you are calculating the same probability, but you cannot actually guarantee that that probability will be the same at these different locations, right? So this is the problem that we have been busy with for 3 years. And I must say, the last year of that 3 years was the most enjoyable year, I must say, because it was where we actually, everything clicked and we were able to understand exactly how is this thing coming about and how are we contributing to solving it. And so here I will simply tell you about one of the ways in which we found, in which we proposed to address this label switching problem. It's an innovative approach, and it's quite interesting. So the first thing that we have to do is we have to assume that the parameters, the global parameters, are themselves non-parametric functions, right? So we just make that assumption, and once we have made that assumption, we can actually see that locally, this varying coefficient, so this model 1, let me just go back to it. So this model here, if we look at it locally, that is at a given local point, it's actually this model here, right? It's actually this model, right? It's actually the Gaussian mixture of linear regressions locally. That's what it is. So that's where the idea actually came about. And the idea is that let's suppose that one of these Gaussian mixtures of regressions, which are obtained at a specific location or a local point, one of these can actually be viewed as conditional distributions for y, right? However, we don't actually observe that information. So since we don't observe the information, what do we have? We have incomplete information. Right? We don't observe something, so there's missing data, missing information. And because there's missing information, how do we solve this missing information situation? We actually restructure or reformulate this model, the varying coefficient model, as a mixture of Gaussian mixtures of regressions, right? So it's a mixture of mixtures. And as a result of that, what we have is we have this model on equation 15, and it gives you lambda. And what is lambda? Lambda is a mixing proportion as well. It represents the probability that the local model T is the one that generated a given data set or a given data point, for instance. So one thing that you have to note is that now we have consolidated all the local parameters into a single model. And the problem that actually gave rise to the label switching problem, or the whatever that gave rise to the label switching problem, was because we were getting local parameters at different locations separately, right? We were getting them separately. The estimation was happening separately, but now we are able to combine everything into a single model. And the only thing that we have to do now is just estimate equation 15, and we will get all the local parameter estimates. Then we have our model. All right, I'm moving quite fast. Let me, yeah. All right, that's 15 is our model, the one that we've just reformulated. So it's a reformulation of the varying coefficient model, and we have 15. It consolidates all of the local parameters into a single model, and then this is what we can do here is by simply estimating 15. That is this model here. We are actually in effect simultaneously. That is at the same time maximizing the local likelihood function. Remember that label switching occurs as a result of separately maximizing the local likelihood function. But now we are able to put them together in a single model, and we can just simply use the EM algorithm, the classical EM algorithm, to maximize that likelihood function 16. And this likelihood function 16 is actually based on this reformulated model that is a mixture of Gaussian mixtures of linear regressions. And to get the estimates, we just have to estimate the pi, the lambda, beta, as well as the variance sigma squared. And to do that, we simply use the classical EM algorithm. It moves fast. Remember, E, expectation, maximization. Expectation, the expected value of the complete data likelihood. And then at the maximization, we maximize that function. And then we repeat, iterate until we reach a convergence stage. So that's interesting. So that is actually the idea of addressing the label switching problem. And I just want to spend the few time that I have discussing a numerical example that we have in this presentation. So we have a simulation as well as an application. So the simulation is, let's consider two components. So we will be estimating this varying mixing proportion function based on those parameter settings. So we have two components, and our mixing proportion function is given there, and that's what we have plotted there on figure 1. So this is where we will be generating the data, just to illustrate how this approach that we propose, how does it work? How does it perform? What are its performance measures? How do they look like? And how does it compare to the naive approach? And the naive approach will be the one where you actually do not take into account the label switching, where you do the maximization at different locations separately. How much time do I have? So this is where we generate the data, and we will generate three different samples, 200, 400, 800, and we will repeat this process 500 times. And after having done that, we estimate this model, the varying proportion, the varying mixing proportions model. It's a semi-parametric model. Of course, it's that model where only the mixing proportion is a function of the covariate. And so we have the results here in this table. So MBEM is the proposed approach that we have. We called it the model-based approach because of its mixture of mixtures. So that's why we called it MBEM. That's what MBEM stands for, model-based EM. And we have different sample sizes, 200, 400, and 800. And we can see that the average squared errors for the model-based approach, the one that we have proposed, is actually better than what we would actually obtain if we were to use the naive approach. And so our proposed approach actually works well, as we can see. But another picture will tell way too much about what is happening here than the numbers will. And as we can see at the top, what do we have? We have our approach applied to the very same data we have simulated. So this is sample size of 200, sample size of 400, sample size of 800. And this is obtained using our approach, or the proposed approach, to address the label switching. And at the bottom, we have the same 200, 400, 800 using the naive approach. And as we can see, if you were to rely on whatever that's been given here, for instance, somewhere here at this point, it actually says that that data point there, it has a higher probability of belonging to the second, that is, this, it's supposed to belong to the first component or the lower component, but it actually gives it a higher probability of belonging to the second component, which is actually not true. So if you were to use something like this, the results from this, you would actually be making a mistake in terms of interpretation or concluding based on whatever study that you're conducting. So this actually shows that we are actually doing well, or our proposed approach is actually doing well. It's able to solve the label switching problem. So next I will show you an application unless people might actually criticize that, okay, you have simulations, but you don't have an application to see where is this applicable. So I'm trying to get supplement for that situation. And this is an old example, or an old data example, where we are trying to understand the relationship between national income for different countries and carbon emissions for the year 1996. So we have 28 OECD countries. And the idea of this study, initially when it was done, it was 2006, I think. They said that they recognize that there are two groups, or they recognize two latent groups. However, you can't actually point them out there. We can't point out which country belongs to which group. So as you can see here, if we look, we have a group of countries here where, as you increase the national income per capita, the CO2 goes up, it accelerates, it shoots up way too much. And then you have other countries here, whereas national income goes up, the CO2 seems to be going a bit down. So what we will be doing here is we will be fitting the varying coefficient or the varying mixing proportions model that we have spoken about so far, and we will compare it with the traditional Gaussian mixture of linear regressions. So here we actually say that we have two components. However, we can't actually see them here. This is the data, we've got it from the population, but we don't actually know which country belongs to which latent group or group of countries. So we will use the model to uncover those groups within this data set. And this is actually what is amazing about mixture models. You don't actually do anything, you just fit the model to the data, and voila, it gives you the results, right? So what we did is we fitted a varying mixing proportions model, semi-parametric. So that's the first row there, and we can see that Schwarz's Bayesian criterion, which is the BIC, as it's known, is actually the lower one between the Gaussian compared to the Gaussian mixtures of linear regressions. So our model is actually better, or the proportion, the varying mixing proportion model is better than the Gaussian mixture of linear regressions. So by actually saying that the mixing proportion is a function of national income, that is, as you increase national income, the probability, the likelihood of belonging to a specific group of countries, it actually changes, right? That is the assumption that we're making. And the model that we have there at the top row is the one that is actually the best. And that's the one that is making that assumption. And we can see below here, we have, so the first column there gives the fitted functions. And we can see that it actually fitted two linear regression models. We have one and we have another one there. And we can see that there are a group of countries here. As you increase their national income, the CO2 emission actually goes up, which means these are the ones that this is 1996. So I guess it's to be expected. Industrialization was taking place then. So it's something that's normal. And here we have other groups, another group of countries where when their national income increases, their CO2 emissions go down. So this is the results that we get without actually tampering with anything. They're just simply fitting the mixture of regression models using a varying mixing proportion. So these two columns here, these two figures, this figure here is the mixing proportion function. It's a mixing proportion function as a function of national income. So it shows that as national income increases, what happens is the probability or the likelihood that you will actually belong to this group of countries that are polluters here is actually decreased. So this is actually positive, right? It's positive. It's showing that as national income goes up, it's less likely that you will actually find yourself in the polluting nations group. Whereas this one says that if national income goes up, it's more likely that you will find yourself with this good group of countries. Good. So these are the results that we obtained from this application using a semi-parametric Gaussian mixture of regressions with a varying mixing proportion, where the varying mixing proportion was a function of GNP. The likelihood of belonging to a specific group was actually a function of a GNP. So I would like to conclude what I am talking about here, and I will just circle back to the beginning of what was the presentation all about, right? And what were we interested in? So we were interested in estimating mixtures of non-parametric mixtures of regressions with non-parametric parameters, non-parametric functions, and we identified the label switching problem when estimating the non-parametric functions. And we only focused on a single model, right, where the mixing proportion function, that is the probability of belonging to a specific latent group, is a function of some covariate. And we say that it's a smooth function. So it's the only one that's non-parametric. And we are interested in estimating this model, and we identified the label switching problem that occurs. And we proposed a new idea of how to address this problem. And so that was what the presentation was all about. And I just want to talk about a few things that we are still, at least a few things that I'm still thinking about how to extend the results of this research. And that is applying these methods to more flexible models. That is, for instance, you can say that let's consider more than one covariate, because here we consider just a single covariate as a function of the mixing proportion function, right? So let's take into account various covariates. Let's say in addition to having family income in our wages and years of experience example, we also have the age of the individual, where did they come from, and so on and so on. So let's include more covariates, and let's try to fit the model using a non-parametric approach. Of course, that will require some working in terms of the functions. How do you define them? We can use additive functions for that purpose. Another thing is, as you noted at the beginning, if your response variable is continuous, then you are actually left with using the Gaussian mixture model. But if your response variable change is different, it's discrete, let's say it's binary or it's a count, then you are in the generalized linear modeling framework. So we can extend the ideas to something like semi-parametric logistic mixtures of regressions. Right? And lastly, it's something about extending the ideas to handle outliers. So how do we handle outliers? Outlying observations, observations that do not belong with the rest of the group. So how do we control, or how do we account for those? What I'm trying to say, how do we account for those observations? I know a colleague of mine who's working on some innovative ideas on this situation, but in a parametric setting. So I think at some point we might extend ideas that we have here to the non-parametric, joining with his ideas. So that's a bit of marketing from my side on what is exactly what are we doing currently and what are we thinking about. And of course, there's more. And so these are the highlights of what we are thinking about. So I would like to thank my sponsors, in fact, our sponsors as the team, the research team. We really did this as a team together, and these are our sponsors for technical as well as financial support. And if you're interested in knowing more about the topic, please contact me. That's my email address. Thank you for listening.
Thank you for an interesting talk. We have a few minutes for questions. Are there questions in the chat? Or would any of the online audience like to speak up? Okay. There are no questions in the chat. So how do you determine how many different Gaussians are being mixed?
That's actually something that you have to, it's model selection. For model selection, you can either use information criteria, there's the type information criteria, or you can use cross-validation. So by just taking your sample and just splitting it into various parts and calculating the error. You're trying
use different.
Yes, you're trying out different K values. So it's a K1 up until 5, and you're seeing which one gives you the smallest error. Okay. And you take that. That's the typical way of
You're not starting with any a priori assumptions.
No.